Hello everyone. So in this lecture we will be understanding or learning about why we need to use solid mechanics and why we are learning this subject. So in the context of mechanics is the area of physics which is concerned with the motions of different bodies. These bodies may be rigid bodies or deformable bodies. So in the mechanics we used to study about two types of bodies. One may be a rigid body and another is a deformable body. In the rigid body, the mechanics of rigid body has, you already know this in your first year course of engineering mechanics. In the rigid body, you know that you used to do two types of analysis. One may be statics and another one may be dynamics. In the statics and dynamics, the behavior of the rigid body is seen. So if we define these two types of bodies in the larger aspect, I can say that if you go by the textbook definition, the rigid body is said to be something, a body, when a particular load is applied on the body, then the body moves and all the points inside the body, they remain at a specified distance after the force is withdrawn. So if there is a body like this and there is some kind of forces or moments are being applied on this body, and we know that we can discretize the body in different points, can be said that body may be composed of different points, then all these points move along with the rigid body and the distance between these points remains the same. This is the wider definition of the rigid body is. But it can be said that in a much easier words, it can be said that the rigid body does not deform. This is what the definition means. So even if the forces are applied on the rigid body, the body does not deform. In fact, the action of these forces is to move the body or to analyze the body. This type of science is called as rigid body dynamics. In these two types of studies are there, statics and dynamics. So you know that in statics, what you used to do, you sum up all the forces acting on the body and equate it to zero. This is what the action of statics is. In the dynamics, you sum up all the forces and you equate it to mass times acceleration. Obviously the mass is also summation. So these types of dynamics, the statics and the dynamics part, you have already learned in your earlier classes. So this is the prerequisites of this course. Let's come to the deformable body. In the deformable body, so other part is the deformable body. This may be of usually of the types in which the matter exists. So matter may be existing in types of solid or liquid or gas. So the mechanics of the solid body is known as solid mechanics, and the mechanics of the fluid or liquid is known as fluid mechanics. So you will be studying both these subjects in this section in this year, but in this class we will be studying more about the solid mechanics. So basically what the aim here is to know about the response of the body. Response of the body in terms means that when the forces are applied on the body, what is the response of the body. In the rigid body mechanics, what we did, we tried to analyze the mechanics of the body, how the body moves, how the body remains stationary, when the different forces are applied. However, in the deformable body cases, in the solid mechanics, we'll be learning about when different forces are applied on the body, how much deformation the body possesses, how much deformation is induced inside the body, or how much strain is induced inside the body, how much stress is induced inside the body, how the body reacts to it, how there is different changes occurring inside the body. So all these terms that I have taken, stress, strain, etc., these all will be learning in this section. So now we will look upon what is stress vector, what is stress at a particular point, and different states of stresses. So to start with, let's take a very simple example of a beam that is loaded. Let's say we have a beam, and this beam is loaded by a load P. When this beam is loaded by a load P, there is deformation occurring in this beam. The beam deforms in this somewhat in this way. So this deformation occurs because the body reacts to it. The body behaves under the action of the load. So this process is somewhat similar to Newton's third law of motion, which says that to every action there is a reaction. So what is action here? Action is the load P. And what is reaction? Reaction is offered by the body. The body reacts to it. And this type of reaction is called as stress. I can define it in a more precise way. These are the internal resistance occurring inside the body. So stress occurs when there is some load acts on the body, when there is the tendency of the body to resist that load. So the load is resisted by inducing stress. So the reaction is stress. To see what stress is, to see the stress, I would like to cut this portion. Let's cut this portion in this section. Let's cut this beam at a particular section, XX, and let's say this is a 3D beam. Let's say the beam is 3D, and let's cut a certain portion of this beam. So when I cut a certain portion of the beam, this portion is somewhat like this. This is somewhat the cut portion of the beam. If I cut it from two sides, then this is the cut portion of the beam. The load that is being applied here is distributed throughout the beam. So this part will also be loaded with some load. So I would like to say that let's say that there is some load. Let's say the part of load is here, and that load is delta P. Delta P is a part of the load applied on this beam. Then let's consider the area on which we are applying this load delta P, and the area is very small, somewhat like this. We can say this, that the area is delta A. Then the applied load, the ratio of applied load to the area is the stress. So stress is the ratio of load upon area. We now know that the load has a units of Newton and area has a units of meter, so meter square. So the unit of stress is Newton per meter square, and is also called as pascals. So now we know what stress is. Stress is the internal resistance or internal reactions occurring inside the body. And using the formula, we have said that the stress occurs at a particular, at each and every point inside this body. There is a load occurring, corresponding load, and corresponding to that there occurs some stress. But this definition is kind of incomplete, because as I reduce this area, this expression becomes invalid. So this expression of stress is more complete when I put a limit here. Limit delta A tends to 0. When the delta A tends to 0, then delta P by delta A is the stress. So my stress is ratio of load upon area. And what this expression says, as the area is reduced to a point, that means as delta A tends to 0, as the area is reduced to point, you have the stress definition coming up. So if I analyze this, that means if I unzoom it, it is actually a certain point. So at this point, since stress is a vector, there is some kind of vector coming out of this point. Some kind of vector coming out of this point. Let's define this vector as T. Now I would like to again zoom this. Let's again zoom this. If I zoom this, I'll get this cube again. So there will be a vector coming out from this also. From this cube, there will be a T vector coming, and this is a stress vector. So I can say that the stress vector here is T. Now we know that this cube is cut on different faces, like it has this face, it has been cut on this face, it has been cut on this face, it has been cut on this face. Like this we have extracted this cube. If we unzoom it, it becomes a point. If we zoom it, it becomes like a cube. It will have 3 faces. So to distinguish each face differently, I would like to give the name to each face, and I would like to give the name by pointing it a normals. So let's say we have a normal N. We have a normal N here also. We have a normal N here also. So how to distinguish between these normals? We can do this by using a coordinate, a Cartesian coordinate system. So let's draw this again. Let's draw it here. Let's say this is X, this is Y, and there is one more Z direction here, and your cube is placed here. Okay, so this is your cube. I have zoomed it more for you to see it correctly. So now, since I have only N here, I can give the specific name to these faces. Let's give a name to this normal, NX along the X direction, NZ along the Z direction, NY along the Y direction. 3 normals. So the stress vector that was coming out from this, like this T will be having three components: Tx along the x direction, Ty along the y direction, and Tz along the z direction. I think you are keeping up with me. The traction vector T that was at a particular point has three components: Tx, Ty, and Tz. These Tx, Ty, Tz may be not along this normal. They may be anywhere oriented along this. So this Tx, Ty, Tz may be anywhere oriented along these faces. These are the three components. The orientation depends upon the magnitude of its components. So what will be its components? It has three components. So each of these Tx, Ty, and Tz will be having a normal component along the normal and will be having a shear component along the other two faces. So it will be having a normal and shear components. Let's talk about these normal and shear components. Normal component will be along the normal direction. So let's give the name to these components. Let's say that along the normal in the x direction we'll be having sigma xx. This sigma is a term that is used to define the component of stress, and xx are the indices, where the first index means that it is along the normal nx and the second index means that it is along the x-axis. The other two components will be shear along the other two directions, that means along the y direction. So we will be defining the shear like this. This will be tau. We will defining the shear by tau and normal by sigma. So this will be tau. First is x along the x and the other direction is y. That means it is going in the y direction. First index is the normal direction. Normal direction is nx. It is along the x. And the other direction is along the direction of the vector. The direction is along the y. Let's talk about the third one. The third one is in the z direction. So its value will be tau. Again, since it's a shear, tau along the x, and then it is going in the z direction or z direction. So these are the three components. So your Tx will be having these three components. So your Tx will be having these three components. Which are these three components? Tx will be having sigma xx, tau xy, and tau xz. Let's talk about this face. This face is recognized by its normal and y, and it will be having a stress vector Ty. So Ty will be having three components on this face. The first component will be along the normal. We'll call this at sigma yy because it is along the y. The other component is tau yx, this term yx because the normal is along the y and the direction pointed is along the x. In the z direction, tau yz. So my Ty will be tau yx, sigma yy, and tau yz. Then I can say that it may be Tz. Tz will be recognized as along this sigma zz, and then we will be having a x shear and this here. You do it by yourself. What will be these values? These values will be tau zx, tau zy. So this will be having tau zx, tau zy, and sigma zz. So as you can see, these are important now. This you have seen. Now this is important. Just look at these things. These are the components of a traction vector T. So the stress vector T has three components. These are the vectors. These are the vectors Tx, Ty, Tz. So T was a traction vector and it has three components, Tx, Ty, and Tz. And these three components itself has three more components. Tx has individually Txx, tau xy, and tau xz. Similarly, Ty has three components, Tz has three components. I can more precisely put nx, ny, and z over the top of this to say that Tx belongs to along the normal. Tx is represented by the face, cut face nx normal. Ty is represented by the cut face ny normal, the cut which is oriented along the y direction, and Tz components are represented by nz. And this T vector can be shown like this. That means it is n normal dependent. So just to reiterate it, just go back a few classes of your 12th. In your 12th class you have seen you have three types of things. You have scalars, which has magnitude but no direction. Then you know about vectors, which has magnitude plus direction. Now, what type of class you will associate to these things? The T is a vector because it is composed of three vectors, Tx, Ty, and Tz. Just to know this, that the scalar, if this is T, the scalar is represented by like this T. If it's a vector, it is represented by indices like this Ti, where Ti means Tx, Ty, Tz, or it may be T1, T2, T3, or so on. I may be 1, 2, 3, X, Y, Z, or anything. So vector has three components and it is represented like this. So definitely this is a vector and the traction is a vector. This is a traction vector or stress vector. So these are the components of the traction vector, Tx, Ty, and Tz. They are also vectors. But what we will say to these things, sigma xx, tau xy, tau xz, yz, yy, yz, and so on. There is a higher class to this. After the vectors, we have a tensor, or more precisely, second order tensor. So we have a concept of tensor and we used to associate order to it. That means a scalar is a tensor of order 0. Vector is a tensor order 1. Order is represented by the index. Here there is no index, so 0. Here there is one index to the vector, so it is 1. And there may be a second order tensor like the stress. Sigma xx, tau xy. These are the second order tensor. Or similarly, we have strains also. Epsilon xx, epsilon xy. We'll talk about strain later, but we have a stress or strain. These are second order tensors. What is meant by second order tensor? Second order tensor represents some kind of two directions. A vector represents a magnitude v, let's say v velocity equals to 250 meter per second. So it has a magnitude of 250 and is oriented at particular direction. So vector is oriented at a particular direction. Let's say this direction is theta equals to 30 degrees and the magnitude of 250. But what about the tensors? So tensors will be oriented along two directions. So technically I cannot show you the tensor because I cannot show you anything that is oriented along two directions. But what does that mean? That means that sigma xx actually is having what was this x? This x represents the normal nx and the other x represents the direction. So it represents the normal's direction and its own component direction. So it represents two things. So you cannot represent a stress like this, sigma xx. This is wrong. You cannot do that. Stress is a second order tensor and its representation is done in a form of matrix. We'll talk about this now. So just to say this, these types of things like these components of the stress vector, this was tx, ty and tz. If you evaluate your stress vector from this, what these will be? Your vector, your stress vector will be the stress component times the direction in which the normal is pointing. Normal direction. Your stress component plus your normal direction plus the other stress component and the normal direction plus the other stress component and the normal direction. So if we add up these together, how this will look like. So I'll make sure that you will be able to see this. So just focus on these terms. So our traction vector T, which was having a particular cut along the orientation N, has three components: Tx, Ty, Tz. And these three components will be having nx, ny and z. Further, I can say that these three components, let me write it in a more precise way, then I will try to accumulate them. So let's say, what is Tx? What is Tx? Tx is the sum of the three components. So each component, like we said here, stress component times the particular normal direction. So Tx will be your stress component, which is first is, let's talk about this, sigma xx times the normal nx plus tau xy times the normal, which is the normal along this ny. This is not nx. The normal along this is ny. what I said here, normal along the direction of the component. So normal along the direction. So okay, you will be able to see this tau x y and z, sorry, and z and y plus tau xz and z. Similarly, t and x and y will be, this will be y. So tau yx along the nx times sigma yy and y plus tau yz and z. I request you to write down by yourself, so you'll be able to communicate with me more precisely. Tz will be nz. This will be tau zx nx, tau zx nx, sorry, tau zx along the x direction plus tau y, sorry, tau zy and y, tau zy and y plus sigma zz and z. So we have three components in each of these vectors. So these are the vectors and these are the tensors, and this is the vector, second order tensor and a vector, second order tensor and a first order tensor, first order tensor, second order tensor, first order tensor, or you can say vector, second order tensor, like this. This can be further rewritten as t, tx, ty, tz. Let me do this to you so that you can see, and then put them in a matrix form. Matrix sigma xx, tau yx, tau zx, tau xy, sigma yy, tau zy, tau xz, tau yz, sigma zz, and the normals nx and y and z. So this represents the complete state of stress at a point. What is this? This is a stress vector we were about to discuss these three things. Stress vector, now we have seen what stress vector is. Stress at a point. This is a complete state of stress at a point. I can write this in a more concise way. You can write this like this: T equals to, consider this as sigma or Ti, sigma ij and j. You can write this like this: Ti equals to sigma ij and j. I will be having three components: x, y, z, and j will be having three components: x, y, z. Let's put some condition to it. If I equals to j, this means normal stress. If I not equal to j, this means shear stress. Isn't it? It looks very easily. That means you can extend this. Put I equals to x and put I equals to x here. Put I equals to x here. And then put x, y and z. Arrange them in the order, you will get these three equations. So when you put I equals to j, that means xx, sigma xx, sigma yy, sigma zz, will be getting normal stresses. These are normal stresses. And the other ones are shear stresses. Let me put it by other pen. These are normal stresses and these are not working. These are shear stresses. And these are the normals along the cut faces nx and y and z. So this equation is a Cauchy's equation, and it is said that this represents a complete state of stress at a particular point. That means all these components represents complete state of stress at a particular point. And this matrix is said as stress tensor. A stress tensor. So what is the stress tensor here? Sigma ij. Sigma ij is your stress tensor. Sigma ij is your stress tensor. So just remember this equation, Ti equals to sigma ij nj. This Ti represents, and sigma ij along with this represents a complete state of stress at each point of the body. That means if you have a beam and it was fixed, and let's say it was a 3D beam, then each point, and it was definitely being loaded by load P, then on each point we'll be having a traction vector T, and this will be traction vector T depends upon the normal, the type of normal it is. That means the type of cut face exposed to you. On this face, the stress vector will be different. On this cut, the stress vector will be different. On this cut, the stress vector will be different. All these cuts, the vector will be different. So this is what the 3D composition is. In all these cuts, when we cut this body, the stress vector that originates or induces on this beam like this will be different on each of the cuts. So we are interested in finding the stress, that is, or the point at which the maximum stress occurs. Because when we can find that point, we can find that plane along which the maximum stress occurs, then we can compare that stress to the yield stress of the body. That means the stress at which this bar or this beam will fail. If we compare them together, and if it is more than that, then we can already analyze previously in advance that our beam will be able to fail. So all these components are there. This is the 3D representation of the same. Further, I would like to add up to this that these components of the stress tensor is symmetric. What do I mean by that? I need one more page. What do you mean by that? That sigma ij is symmetric. Sigma ij symmetric. What does that mean? That means sigma ij is equal to sigma ji. That means the stress tensor that we have is symmetric. That means tau xy is equal to tau yx. Tau xz is equal to tau zx. And tau zy is equal to tau yz. So instead of the 9 components we have, 3, 3, 3, 9, we have 6 independent components. The stress tensor has 9 components. So instead of the 9, after applying the symmetry, we will be having 6 components to find. If we can find these 6 components, we can find the traction vector T, and we can find the stress vector along that plane. So this component, 6 components are required. So I would like you to be left as an exercise to you to define that sigma ij equals to sigma ji. That means tau yx is equal to tau xy, and tau zx is equals to tau xz, and the other one tau xz, tau zy is equals to tau yz. I would like you to prove this. The proof is very simple. What you have to do, you have to create again that famous, very well aware cube, and you put them the shear components. You can, okay, don't take the 3D one, just take the 2D one. Just take the 2D one and put the shear components. Tau yx, tau xy, and put the other 2 shear components here, and you sum them to 0 like you do in your mechanics. Take a certain point, take a moment of all of them, and prove that the moment along this point, let's say this point is A, equal to 0. Take the moment of them. Take these as dx, dy, and you will be able to take the moment of them. Put them together, you will see that you will be coming out with tau xy is equals to tau yx. So it will be easy to prove. I would like you to do this. So I will move forward. I'll move forward to the last one, the states of stress. What does I mean by that? Just to reiterate it, what is meant by state of stress? States of stress. I have, let's say, a beam or a rod. This rod can be loaded in different positions, in different ways. I can do a tensile loading, where I can put or pull this along this. So this will be a positive increment occurring in this bar. In this bar, I am loading this along the axis of this in a tensile manner. So this will be a tensile loading. And let's say rather than P, I can put stress sigma. I am applying the loading along this direction. So let's say this is the x direction. So I am applying the loading like this. So what will be my stress tensor for this loading? My stress tensor will be, I have applied only this type of loading. So my stress tensor is sigma xx, x along the x direction, and the other components are 0. If I would like to apply it only along the y direction, loading, let's say I have applied the loading along the y direction. I have applied the load along the y direction. Then the stress component will be this is along the x direction. In the y direction, the stress component will be sigma y, and the others will be 0. Such type of loading, and definitely this will be valid for the z direction also. Such types of loading is called as uniaxial loading. Uniaxial loading. And this type of stress that is coming out from this is uniaxial stress. There may be a biaxial stress. That means the bar is being loaded from both the directions, sigma x, and you have applied sigma y also. So in that case, this is a biaxial loading. So your stress tensor will be sigma x, sigma y, and the rest is 0. In a similar way, we can have a triaxial state of stress. In a triaxial state of stress, we will be having a stress tensor sigma x, sigma y, sigma z. Just to say that this is, I have earlier I have written sigma x, sigma y. So you can write, since the indices are repeating, you can write this x in. Just a sigma represents a normal stress. Don't need to write a repeating index xx and yy again. You can write it, doesn't matter. And the other shear components are 0. This is called as triaxial state of stress. This is biaxial state of stress. This is uniaxial state of stress. Now there may be a pure shear. That means we are loading it in such a way, we are loading the beam in such a way so that only the shear occurring between the load. So in the pure shear case, that means a beam is loading in a shear direction in all the four faces, in all its four faces. So for a pure shear case, we will be having a stress tensor like this: 0 along the normal, and we'll be having tau xy, tau xy, tau xz, tau yz, tau yz, tau xz. Remember that these are equal, so they remain the same, because you have to prove this. To prove this, that this is called as, this equaling of the shear is called as equality of cross shear. Equality of cross shear. So such type of loading is called as pure shear loading, in which there is no normal stress, only the shear stress components are present. Okay, so for now we will stop here, and we will meet in the next lecture.